Welcome. Today's lesson is entitled Properties of Limits and One-Sided Limits. The front side of your notes worksheet deals with limit properties, and the back side of your notes worksheet deals with what are called one-sided limits. So we'll develop a few ideas, do a few examples, and this offers a nice continuation to the previous lesson where we introduced the concept of limits. So let's start it out with the investigation at the top and see where it leads. The investigation says, use a table to find the following limits. Make a connection between the limits and the function values at A. All right, so two different things, the limit first and then the function value. Let's start with the limit. So I've got the limit as x approaches 4 of x plus 2, and that equals something. And I'm going to create my little table just like I did yesterday. So what I'm going to do is come at 4 from both sides, from the left side and from the right side. So I'm just going to choose a couple numbers that are close to 4, 3.9, get a little closer, how about 3.99? And you know the drill at this stage, totally arbitrary, really just getting a sense of it. I could keep going, but I'll leave it at that. And then I'll come at it from the other direction too, and I'll start pretty close there. I've got a number in mind, something like that. Again, just kind of working through nice and easy there. Okay, very good. So coming at 4 from both sides, I'm going to put those values into the function and see what happens to my function values. So if I put 3.9 in, 3.9 plus 2, easy as can be. 3.99 plus 2, again, shouldn't be a big deal. Same, got that. And I got the left side taken care of pretty fast, as we can see. All right, let's keep it moving. Other side, I'll start from the outside here. 4.1 plus 2 looks like 6.1. 6.01, coming a little closer. 6.001, all looking great. And you can tell without a whole lot of issue here that the numbers seem to be getting infinitely close to 6 from both sides. And so the limit, of course, as x approaches 4 of x plus 2 equals 6. No big deal. Now, guys, the secondary piece. What I want to know is what happens at 4. So what happens at that number that we sort of worked on in the table? Well, what is f of 4 here? Well, if you notice, if I actually treat this as my function, and my input is 4, 4 plus 2, of course, is 6. And you see, it shouldn't be a major surprise in this particular case at least, but the limit is equal to 6, and the function value is equal to 6. Keep that in mind. Two different ideas, same answer, of course. All right. I will go rather fast on this one, if that's all right with you. I might need the calculator for it, but let's do the same thing. The limit as x goes to 6 of 2x squared. And so I'm going to go ahead and do my little table, x and f of x. One more time for good measure here. Do it with me if you would, please. So 5.999, etc. right there. And then same deal, guys. I'll just come at it from the right-hand side. Just my typical numbers. Nothing special. Coming at 6 from both sides. I'll go ahead and grab my calculator and put those in, and let's see if we can go ahead and get a few values. I'm going to bring this on over just so I can go ahead and back and forth on this. So here we go, guys. 2 times 5.9 squared. Let's clean that out one more time. 2 times 5.9 and squared. There we go. So 6962. Let's get that up there. Good. I'll keep it going. So 2 times 5.99 and square that, of course. And I've got 71 and change on that. I'll go ahead and just round a little bit. Shouldn't be a problem. And you can see I'm working pretty fast on this. So I've got 2 times 5.999. I'll square it. Getting the hang of it, I've got 71, about 9/8 there. Again, theoretically, I can go further and further and further. Let's go ahead and get that other side taken care of. So 2 times 6.1, and I'll square it. There we go. So from the other direction, I've got about 74.72, I think I saw. Cool. You're filling in the table with me, of course. That was 74.42. I'll change that. 2 times 6.01, and square that one. So 72 to 4. Put that right here. And this was a 4, by the way, just what I saw on the calculator. Sounds good. And I've got one more to do. And so I've got 2 times 6.001. And then I square it. Good, and I get 72.02, give or take. All right. I think we can kind of draw a couple conclusions. First and foremost, as I look at my function values, they seem to be approaching 72, and I hope you agree with me on that. So we would say the limit as x approaches 6 of 2x squared is equal to 72. Now, separately, guys, let's put in 6. And so look at the function, of course, and I've got 2 times 6 squared. So what happens if I actually put the number 6 in? Well, 2 times 6 squared, of course, is 72. And you notice we did 2 different ideas, essentially. One being a limit, sort of what's going on as we get closer and closer to 6, and then what happens at 6, and we end up getting the same value. And that's great, because what we want to start to do is create a little shortcut for ourselves when we find limits. This table, it's wonderful, but it does take a little time. So let's draw a conclusion from this. Now, in calculus, you will dive into this quite a bit deeper. So this is the extremely abridged version. But there are, a dozen at least, a variety of formulas and properties that allow us to shortcut this a little bit here. So there are a variety of formulas and properties for limits that allow us to find the function value. And again, it's really a separate idea, but it's going to allow us to find the limit by working with the function value here. So let me make sure I phrase this correctly for us. So for limits that allow us to find the function value at a, like I did in the previous example, and which is equal to the limit. All right, that's what you're going to throw in this piece right here. So rather than doing this whole table right here and seeing, oh yeah, it looks like they're approaching 72, that's our limit, what we can do is try to put 6 actually into the function itself, and when 6 produces 72, then that is equivalent to the limit. So the function value, which is obviously pretty easy to calculate, ends up being the value of the limit. Okay, great. So let's do example 1 to kind of solidify that idea, and then we'll go for the next step. So example 1, find each limit. So it's the limit as x approaches -3 of x plus 16. Now rather than doing a table and working with numbers to the left of -3 and to the right of -3, the good news is we can actually just put in -3. And so -3 plus 16 is just 13. And so because that is the function value at -3, it is also the limit as x approaches -3. I hope that makes pretty good sense. Obviously, we're trying to find ways to shortcut it, and that's exactly what we did. Okay, next one right here. Limit as x approaches 7 of this nice quadratic function right here. And so rather than putting in 6.9 and 6.99 and numbers just above 7, let's just put in 7. And by putting in 7, we're able to calculate its limit as well. Okay, so I do 7 squared minus 10 times 7 plus 5. I've got a -16 on that. My apologies for not actually bringing up the calculator to do it, but did that quickly mentally. That'd be great if you can confirm, but 7 squared minus 10 times 7 plus the 5, I believe we're looking at the -16. All right, next course of action here is to take letters C and D. So let's do C. Limit as x goes to 4 of this 3x minus 5 cubed. Perfect. Sorry for being redundant, but again, rather than putting in numbers to the left of 4 and to the right of 4 to find the limit, what we're allowed to do here is let's just put in 4. So I have 3 times 4, which is 12, minus the 5, which is 7, and 7 cubed. I've got 7 cubed at 343. Nice. And let's see what we have on this last one right over here, letter D. Limit as x approaches 2 of this rational function right here. Let's go ahead and see what we end up getting. We're allowed to put 2 in, so 2 squared minus 4 times 2, and then plus the 1. So I've got 4 minus 8, and then plus 1. I'm getting a negative 3 on that. And down on the bottom, 3 times 2 is 6, minus the 5. That's positive 1. And so as you can see, it's just going to be negative 3. So great, huh? Nice and easy. In order to find the limit, we put in those values, and that tells us what's happening as x gets infinitely close to that number. It's saying, in this case, sorry for the redundancy, let me come back to letter A for just a sec. When I'm looking at this, I'm asking myself, what are the function values getting closer and closer to as x gets closer and closer to negative 3? Well, the function values are getting closer and closer to 13. All right. Hope that makes pretty good sense so far, where those properties really just allow us to put in the number that we want. Now, here's the unfortunate thing. It doesn't always work. So if the limit of the denominator is 0, you must rewrite the expression before you can find the limit. And so a couple different ways that we're going to go about doing this here. And so let's go ahead and take a look. Example 2, we've got an A, B, and C. And this is the type of algebra that you're going to work with in this next piece going forward, in our little calculus unit. So here's what I'm thinking. We want to take, for letter A, the limit as x approaches 1 of this nice rational function right here. And it looks pretty harmless. 1 goes into the top, and 1 goes into the bottom. And I hope you notice here we have an issue. When 1 went into the bottom, I end up getting 0. And as a result, does this produce any type of number that would allow us to say that that's the limit? No, because when I put in 1, I'm not able to do the calculation. I get it as undefined. And so what we need to find a way to do, we need to find a way to get around that. And so this is how it plays out. Let's go for it. Just good algebra. That's what you'll see really the rest of the way here. And so in this case, as I look at the top, that's something I can work with, because the top actually factors to x plus 3 and x minus 1. And down on the bottom, of course, I have that factor of x minus 1. And we've seen this, of course, before, where this as a common factor does cancel out, and that goes away. And so now what I'm left with, for all intents and purposes here, I've got the limit as x approaches 1 of x plus 3. Now, everybody, can I pull the trigger on the 1? Can I put the 1 in for x and actually get a value? Yes, I definitely can. And so I'll go ahead and do that, of course. I put in the 1, and now I get 4. And so that's the situation that we're after, is we're trying to put this number in. All these properties are really saying, hey, look, you want to put that number in. But if you can't, then you have to work around it algebraically until you can. And this, again, is the exact type of algebra you're going to see when we take the next step in our little unit here. All right, so I hope that works. Couldn't do it here, couldn't put 1 in here, but we can put 1 in right here. And when we do, we get 4. And that's the limit. And just FYI, if I made a table here, not that I'm going to, but if I made a table coming at 1 from the left and coming at 1 from the right, we would see this, guys. The function values would be getting closer and closer to 4. All right, perfect. Let's go ahead and do the same thing here. So in this case, I'm looking for the limit as x approaches 3. But look, I've kind of fractions and fractions here, and you know, this is the big fraction line. And immediately I see I'm trying to put 3 right in here, and unfortunately 3 minus 3 is 0, and so it just doesn't work. So let's find our way around this. Now it's up to you. You know, I'm visual and I like symmetry here, so I'm going to put both of those over 1 separately. If you want, and it works just as well, you can just do one big fraction line and put the x minus 3 over 1. I'll leave that up to you. But we've seen these compound fractions before, where I'm allowed to mess around with it a little bit by multiplying each of those individual fractions by the LCD. So guys, let's look at the denominators. 1, 2, 3, and 4 denominators. I'm hoping you can pick out an LCD of 3x by looking at those 4 denominators. So again, we have seen this before. My hope is that that'll make pretty good sense when this comes through. And let's clean this up and see what happens. Again, I want to put 3 into the expression. I can't do it right here. So let's play around with this and see if we can do it. All right, so guys, let's distribute. This distributes into this fraction right here. What happens to the x's? 1 on top, 1 on bottom. They cancel. X's cancel. And so I get 1 times 3, which is 3. And that was the point. We want to get rid of the denominators here. Same thing. Here's the minus. Bring it down. Good. Now I repeat. This distributes into this fraction right here. What happens to the 3's? 1 on top, 1 on bottom. 3's cancel. And I have a 1 times the x, which is just x. It's a great, effective way to clean out compound fractions. Okay, now this one right here, does anything cancel when I distribute the 3x into this fraction? No, because it's just 1 down there. So 3x times x is 3x squared. Same thing here, last time. 3x times 3, and should be 9x. All right, now here's the deal. I will tell you, again, I want to put the 3 in. I want the little equals on the back, putting in the 3 in, and I want to get an answer. But unfortunately, if I put 3 in, I still have 0 on the bottom, not to mention also 0 on the top, so I'm not ready yet. So we need to go further. Let's keep wanting to take the limit as x goes to 3, but let's simplify a little bit here. And guys, simplifying fractions really comes down to factoring. So let's see what I can do down on the bottom. I'm going to take out a 3x, and I get x minus 3. Okay, that's actually pretty good. Now, I am curious what you see. It's close, isn't it? This is an interesting one because I have that factor of x minus 3, which is definitely the issue. I would love for that to go away. I would love to eliminate that piece. If you look at the top, I have not x minus 3, but 3 minus x. Is there a way to tweak that top just a little bit, everybody, in order to get the exact same thing here? Yeah. And what we can do is take out the negative 1. So I'll take out negative 1, and this is going to change this to a positive x, and it's going to change this to a negative 3. All right. And now, guys, what happens? X minus 3's go away. And as a result, once they go away, I'm going to write this one more time here just to make sure it's clear. I've got the limit as x approaches 3 of negative 1 over 3x. Now, everybody, can the 3 go in safely? Yeah, it definitely can. Because when the 3 goes in, I just get 3 times 3 on the bottom. And there is some great algebra right there. So we got rid of the factor that was the issue on this 3. And when we did, we put the 3 in. And once we put the 3 in, we get our limit. Wow, that's really great. Again, rather than making a table and doing all that stuff, we work algebraically with it. Okay, very good. Now this one happens to be a very contrived one, this letter C. But you notice the issue. Obviously, I cannot put 9 in. I would get 0 on top. I'd get 0 on the bottom, and that's obviously undefined. And I don't want to do a table. So there's a little algebraic trick or technique, whatever you want to call it, that works with this. So I'll go into that piece. And I have it on your paper here. You've heard of rationalizing denominators before. This little trick is what's called rationalizing the numerator. And we're going to deal with something we've seen before in this course, in previous courses, what's called the conjugate. And so the conjugate of root x minus 3 happens to be root x plus 3. So guys, if you would, root x plus 3 on top and root x plus 3 on the bottom. And again, it's a very, very obscure little trick here, but it does come up on occasion for certain functions, and so that's what we're seeing. Now watch what happens when you do this. So I've got the limit as x approaches 9. Now the bottom I'm going to do first. In fact, I'm going to kind of leave it just like this, just for the time being. There you go. That's all right. What happens on the top? What would you get if I asked you to FOIL the top? And if you look at this, root x times root x is really x. What happens to the outside and inside? Again, you've seen this before, no doubt about it. But I hope you see that the outside and inside cancel. And then on the back end, negative 3 times 3 is 9. And so you kind of look at that and you saw that this x minus 9, especially on the bottom, that was the issue. Well, by doing this little trick, I created the same factor on top, which now, guys, allows it to go. So the x minus 9s as common factors can cancel out. And so now I go the limit as x approaches 9 of 1 over this. Now, guys, again, excuse the expression, but basically I'm looking to pull the trigger on the 9. I want to put that in. That's, again, kind of the moral of the story here. And that's exactly what we're going to want to do when we see some of the utilizations of limits when we move forward in this calc unit. But basically, guys, I want to put the 9 in. Can I put the 9 in successfully here? Yeah. And so the 1 on top, if 9 goes right in here, square root of 9 is 3, and 3 plus 3 is 6. And so the limit as x approaches 9 of that original function right there, guys, is exactly 1/6. Remember what that says. It doesn't say when you put 9 in, you're going to get 1/6. What it says is as you put numbers in closer and closer to 9, the function values are getting closer and closer to 1/6. So a really nice way to work with limits here. You want to put the number in if possible. Okay, guys, let's hit the back side here. These are what are called one-sided limits. Obviously, you can see. This side, we're going to come at the number from the left. This side, we're going to come at it from the right. Just a little notation and definition for this, and then we'll just do our last few examples to kind of put this together. So, doing great. Keep it up. So I've got the limit as x approaches a. If it is a left-hand limit, everybody, there's one little tweak to this. We put a little negative right upper right-hand corner of that a. So this would be the limit as x approaches a from the left. And so that's what we're going to look at. And then of our function, and then obviously equals some number, whatever it may be. And so when we see this from the left, and that's exactly how we would kind of read that, x approaching a from the left, what that basically means, as x gets closer again, closer and closer to our a value, but stays to the left, or less than a. So that's what you're going to write in there for me. That would be ideal. So again, and think about a number line there. If we're coming at it from the left of a particular number, on the number line, those are numbers that are less than our a value. So that's it. So we're basically just taking it from one side. Think of the table. We did it from the left, we did it from the right. Here we focus on just one side or the other. Cool. You could probably imagine what's going to happen here, everybody, so let's get it in. From the right, we have a little plus sign up there. So that's how we would read this. Limit as x approaches a from the right. And you can probably envision what type of numbers in relation to a that would represent. So let's get that in and move forward. Here we go, from the right. That's how we would kind of think of this piece. And so same deal as above, everyone. Means as x gets closer to a, getting closer and closer, but if we're to the right of a, then we're talking about numbers bigger than a. And so this is what you're going to write in. Okay, all different types of functions. We'll probably focus on what we would call piecewise defined functions to really solidify this idea. Okay, good. Well, let's start it out here graphically, and then we'll work with the function represented as an equation and see if we can kind of put some things together. All right, so one or two concepts that are embedded in these examples. So please do them with me, and let's see if they make pretty decent sense. Example 3 says, use the graph to determine the following limits And so in this case, let's look at letter A. We're going to take the limit as x approaches 1 from the left. All right, so only from the left, one side only. Now, again, just if you get an opportunity, I think this is helpful, but just very, very lightly. Let's find where x is 1, which is right here, of course, and let's just, a slight vertical boundary right there might be helpful. You know, it's your call on that. And what we do, and basically what we did yesterday, is we hop on the graph, one particular side of it, in this case, obviously, from the left. So guys, hop on the graph anywhere to the left of this vertical line, and now let's get closer and closer to that vertical line. And just ask yourself, what's going on with those function values? So here we go, we're going up, we're going up, we're going up. Nice. I'm passing 3, it looks like, right there. And again, as I get closer and closer to 1, those y values, vertically, it seems like it's getting closer and closer to 4. And I hope you would agree with exactly that conclusion, that those function values are getting closer and closer to positive 4 as I approach 1. Okay, good. Now, let's go get letter B. The limit as x approaches 1 from the right. So same deal, everyone. Here's your vertical line. Hop on the graph anywhere to the right, and then let's go towards it. So I come at it. I'm coming closer and closer and closer. Doing nice. I'm keeping an eye vertically here. Looks like I'm above 1, getting closer and closer to, what's this vertical piece right here? It looks like getting closer and closer to 2. And so you see, as a matter of fact, in this particular case, from one side I'm getting closer and closer to 4. From the other side I'm getting closer and closer to 2. So the bottom line here is, for a limit to exist, we have to be approaching the same value from both sides. So now, guys, when I say the limit as x approaches 1, this means from both sides. Well, in this case, guys, the left side I'm going to 4, the right side I'm going to 2. Those are two distinct, different numbers. And so as a result, because those two sides are different, we would say does not exist. So the limit in this case does not exist, because our function values are not approaching a particular number as x goes to 1. They're approaching two different numbers from each side. So DNE just means does not exist. And you can see that here. Moral of the story with this one, if these are different, there is no limit at x going to 1. Okay, let's try one more in this particular graph. So in this case, it looks like the limit as x goes to 3 from the left, and x goes to 3 from the right. So let me do just a touch of erasing so it doesn't get in our way here. And let's go find 1, 2, 3 right here. There we go, nice vertical line. And let's see what's going on with this. So hop on the graph to the left. Here we go. So I'm here, I'm above 1, I'm getting down, going down, closer and closer and closer. I'm hoping you're all right that you see vertically it seems like those values are getting closer and closer to 1. So as I get closer and closer to 3 from the left, my function values seem to be getting closer and closer vertically to 1. So I'm going to put a little 1 right here and hope for the best that you saw that. Now, same deal, everyone. Nice and easy. Here we go. I'm approaching from the right. So here we go from the right. Vertically, what's going on? Well, same deal, guys. It seems like it's approaching right about here, which vertically would be 1. And so, in this case, it equals 1. And do you notice when I looked at it from the individual sides, the left side and the right side have the same limit. And so, shouldn't be a great shock here. Mathematically, it's defined. And so as a result, the limit as x going to 3 is equal to 1. Because from both sides, it's approaching the same number. It's approaching 1. So you can see the top row, why we got this as our conclusion. Bottom row, why we got this as our conclusion. Awesome. Let's do example 4, kind of put it together with an equation. So here's what is called a piecewise defined function. My function is defined as x squared plus 6 if x is less than 2, and x cubed plus 2 if x is bigger than or equal to 2. All right, so here's what I'm thinking here. Just starting this out, you don't have to do this on your paper, but here's 2 obviously on the number line. And so I guess I would ask you this with your experience with piecewise functions. I would be approaching 2 from the left. So numerically, just on the number line, here's 2 coming at it from the left. And obviously, guys, think about the numbers that are from the left. You know, here's 1, here's 1.5, here's 1.9, 1.99, etc., etc. Obviously, you can see those are all numbers less than 2, right? Just like we determined above when I gave you that definition. Now the question is, if I was to make a table here and put in numbers to the left of 2 or less than 2, guys, where would it go? Would it go in the top equation or the bottom? Would it go in here or in here? Well, numbers that are to the left of 2 or less than 2 seem to be part of this domain interval right here, which means as a result, they would go in the top expression, I should say, right here. And so if I asked you to put 1.9 into the function, because that's less than 2, you'd put it right in here and get an answer. If I gave you 1.99, that is less than 2, so you'd put it in here and get an answer. Now I don't want to do that. I don't want to mess around with tables again. The properties allow us to put the number in if we can. So guys, let's put in 2. But if for the left-hand limit, do you think we're going to put it in the top or the bottom? Well, again, guys, I alluded to it. We're going to put it in the top. So we're seeing what happens as we come at it from the left. And so as a result, we're going to put in the 2 based on this premise right here. Okay, so 2 squared plus 6 happens to be 10. So I'm sorry for the redundancy, but I do want to make it very clear. If you were to make a table to do the left-hand limit, and you could do that, 1.9, 1.99, etc., etc., all those numbers would go in the top. Our shortcut, instead of putting those values in and seeing what happens to try to draw a conclusion, it's just put in the number where you were thinking. And so we put the number in, 2 squared plus 6 is 10. Okay, let's try this. So limit as x approaches 2 from the right. So again, here's 2, here's to the right of 2. So think of numbers to the right of 2. Here's like 2.5, 2.1, 2.01, 2.001. Those are all numbers bigger than 2. So if I asked you to make a table, where would you put those? Which expression? Top or bottom? Well, those are all numbers that are bigger than 2. And so as a result, it fits this domain interval right here, and we would be putting them right in here if we were to create the table. But we're shortcutting the table. Instead of putting those numbers in, we're just going to put this number in. We're just allowed to put A in. We just put it in the bottom here. 2 cubed, everybody, is 8, and 8 plus 2 is 10. Hope that makes sense as to where we put the numbers. Left side, we put it in the top because left of 2 means less than 2. Right side means we put it in the bottom because those are numbers bigger than 2. And instead of making the table, we shortcut it by putting the A value in. Now guys, the left-hand limit's 10. The right-hand limit's 10. So our answer is 10. Because it approaches the same number, that is the limit by definition. Cool. Interesting mathematics, huh? Pretty complicated. Let's do 5. Same deal, just different function here. 2 from the left, which means, again, 1.9, 1.99. That would be this domain interval. It would be going in the top. Shortcutting, putting those in, let's just put our A value in. Same place as where we would be putting our table values. And so 2 squared plus 5. 2 squared plus 5 looks to be 9. All righty. Let's take the limit as x approaches 2 from the right. So 2.1, 2.01, etc., etc. Numbers bigger than 2. We would be putting them right in here, but rather than doing that, let's put the A value in where we were thinking. 3 times 2 is 6. 6 plus 1 is 7. Excellent. Did you notice the left-hand limit is equal to 9? The right-hand limit is equal to 7. And if the function is approaching 2 entirely different values, can we say that the limit exists? No, it does not exist. So what's happening here is as x approaches 2 from both sides, they're approaching two different numbers. It's not approaching a single value, and so as a result, again, does not exist. All right, last piece, guys, and I'll be rather quick with this. If and when you ever take a calc class, one of the ideas that comes up is talking a lot about continuity. In order to kind of take that next step, continuity is really an inherent prerequisite to it. So I'll just blurt out a few things about it and then wrap this on up. So it says, look at example 3. Is the function continuous at an x value of 1? So let me go back to example 3, and here's the graph right in there. It looks good. And guys, here's the x value of 1. Remember, continuous basically means I don't have to pick up my pencil. But if you kind of look at it, when I'm approaching 1, would you agree with me that I have to kind of pick up my pencil right here and to go from here to here? And as a result, there's this discontinuity in the graph right when x is equal to 1. So I think intuitively you know continuous versus discontinuous on a graph. And I hope that makes pretty decent sense. So it says, is the function continuous at an x value of 1? No. And one of the reasons it is not continuous is because of what we got right here, the limit not existing. So there are three criteria, and I'll be very fast with this piece and wrap this on up. It just says, what does it mean for a function to be continuous at a particular number? So let's go ahead and take a look at it. And these are just things you've been working on really since day one with functions. So in order for it to be continuous at a particular number, it has to be defined at that number. It has to be part of the domain. So A is in the domain. If it's not in the domain, you've seen this before with a variety of functions, obviously we can't talk about continuity. So A is in the domain, and obviously that would mean that when you do f of A, you get a real number. So something along those lines. And again, I think you've kind of worked with that idea before. Now the second thing, to me, which is the big thing, is that the limit exists. So we saw in a situation above where, hey, the limit on the left is not equal to the limit on the right, and so as a result, the limit didn't exist. Well, for something to be continuous, it has to exist. And the last order of business deals with kind of how I started this lesson. We looked at the relationship between the limit, and we did it with the table, and we did it the function value. And guys, that's the case. And this is the big piece. And again, you probably kind of figured this intuitively, but obviously this is just written out a little more explicitly for you. So basically, not only does the limit exist, but it equals the function value at A. And if that's the case, you've got something called continuity on the graph at a particular point. So it's defined here, the limit exists here, see, notice the limit exists, and the function value is equal to that limit. Pretty cool. If you have some more questions on limits, happy to go through it. Again, we're going to go ahead and apply the concept of limits over the next few lessons. So just hopefully you can work with the algebra here and understand a couple of these pieces. Hey, thanks for listening. I'll wrap it up at this stage.